99% of the sun's fusion takes place in its core. Fusion typically requires a temperature of about 100 million Kelvin, but the sun's core is only 15 million Kelvin. So how is fusion even happening? Today, we're going to be talking about quantum tunneling, a phenomenon where objects that don't have enough energy to cross a barrier just decide to teleport instead. When you leave the world of apples falling off of trees and zoom into the subatomic stuff, you officially enter the quantum world. In classical physics, things are certain. You're either here or there. But the quantum world is dictated by probabilities. Scientists model these probabilities using a wave function, and the higher the amplitude of the wave, the more likely you are to find the particle there. In classical physics, if you have an object that doesn't have enough energy to cross a barrier, we are certain it won't cross the barrier. But in quantum physics, if you have a particle traveling towards a really thin barrier with finite height, there's a small chance you'll find it on the other side, even if it doesn't have enough energy to cross. And just a side note, this barrier doesn't have to be physical. It could be the repulsive force you feel when you push together magnets of the same pole. Just as hydrogen particles, they tunnel through the potential barrier of hydrogen bonds to mutate DNA, and also tunnel through the barrier of Coulombic repulsion to create helium in the sun. Let's take a look at an example. This laser is experiencing total internal reflection because it's unable to cross the barrier between the glass and the air. However, when we move the second glass block really close, we faintly see the laser in the second glass. The only way this is possible is if some of the photon particles in the light wave were able to tunnel past the glass-air barrier. This is precisely the quantum tunneling effect. Now, for those of you that are wondering, yes, Newton would be rolling in his grave right now. Particles can't just go wherever they want without enough energy, right? And this is the part where I'm gonna rip apart everything you ever learned in science class. You thought particles were a real thing? Rookie mistake. I know, I just spent 2 whole minutes talking about particles tunneling through barriers. But from the lens of quantum field theory, our world is made up of overlapping fields. And what we consider particles, like electrons and photons, are merely excitations in their respective fields. When excitations can't break through a barrier, they typically bounce back. But sometimes, excitations collapse in a process called annihilation, releasing their energy. It's highly unlikely, but sometimes, this energy causes a new excitation across the barrier, creating the illusion of teleportation. So yes, particles can't go wherever they want without enough energy. But what matters isn't the energy needed to cross the barrier. It's the energy needed to create an excitation. So Newton, you can rest in peace. Okay, wait, does that mean we can finally walk through walls? Why don't you try it out yourself? Actually, I'll save you the effort. It might look something like this. So yeah, unless you're an elementary particle or member of the wizarding world, you can't cross through barriers. At least not yet. But maybe, someday, you will.